Okay, welcome everyone for lecture 2. So today we will talk about the problem of computing the smallest k-enclosing disk. So as I promised, this will be a very short lecture. So what's the problem here? Problem is the following. So this is the setting we have. The input is a set P of endpoints in 2D. Now, find the smallest radius disk. We'll draw a figure pretty soon. Find the smallest radius disk which contains k points of P. Okay, so because this is a course on approximation algorithms, we don't want an exact algorithm here. Instead, the goal here is to compute an approximation. So what's the approximation here? Compute a disk containing k points and having radius at most 2 times r opt. Okay, so now the approximation is on the radius of the disk, right? So what is r opt? Let's define what r opt is. R opt is the smallest radius disk containing k points. So this is the optimal disk which has radius r opt, which contains k points, but we are not interested in computing this smallest radius disk. Instead, we are saying report any disk which contains k points, but its radius should be at most twice the radius of the optimal disk. So this will be a 2 approximate algorithm, right? So to restate the goal, a 2-factor approximation is what we are aiming for here. So I hope the problem statement is clear, very simple. Let's do some visual. So let's draw some bunch of points here. Let's say our k is 5, right? So then, as you can see, very nicely I've drawn a figure where I can say that, this is the optimal disk. This is the optimal disk which contains those 5 points. Okay. So there's some points I want to make before we actually start into the algorithm description. So so this k-enclosing disk problem, right, can be thought of as a generalization of the closest pair problem. Of the closest pair problem. Why? Well, if k is equal to 2, this is exactly the closest pair problem. And that was what we discussed in the previous lecture, but we won't need any of that material here, but still. This is the closest pair problem. Well, so it's a very natural generalization, this problem. So we want to find k points which are very near to each other instead of 2. And this can be thought of this problem can be thought of as a very simple form of clustering. Very simple form of clustering. You just want one cluster where the points are very close to each other. Right? So these are some things which make this problem very interesting. And in general, from a geometry point of view and algorithms point of view, it's a very fundamental problem to ask. Okay, let's move on. So before going into the approximation algorithm, one might ask, okay, if you want to solve this problem exactly, how much time will it take? Well, I'll leave it to the reader. I mean, one point I'll make here is, let's try all combinations, right? That's one way to solve the problem. So if you want to try all combinations, one question you can ask is, how many points define a disk? Well, if you can answer this question, then you can try out all possible disks, which can be an answer to this problem, and then finally pick the smallest one. Right? So I'll leave it to the reader to solve this problem. So yeah, you can come up with a very nice solution which tries all combinations, and then you can further refine this algorithm further to get down the running time. All right. So, but in any case, you can always solve the problem in n to the power 4 time. Can you do better? Well, I'll leave that as an exercise. Okay, so now it's time to jump into the approximation algorithm. So let's talk about the approximation algorithm. And what's the key insight? So this is the key insight behind the approximation algorithm that will be devised. Okay, it's very simple. I mean, once you see it, it looks very simple, but the key breakthrough was in actually coming up with this insight in the first place. Okay, so this is the key insight. If we succeed in finding a point inside the optimal disk, then we are done. That's my claim. So the thing is, we don't know what the optimal disk is, but if somehow we can succeed in finding a point which lies inside the optimal disk, then we're done. Why do I say that? Okay, let's look at some examples here. Let me carefully draw two figures here. So let me draw a few points here. Again, I'll try to set k equal to 5. And I'm saying, so this is the optimal disk. All right, this is the optimal disk. So its radius is r-opt. Okay. So now let me pick some point inside the disk, which is perhaps not one of the input points, but some other point. Okay, so let me pick this point. All right. And now let me draw a circle or maybe a disk of radius 2 times r-opt with this red point as the center. Right, so maybe it'll look, okay, it'll look terrible right now. But believe me, this is also a disk, which is not to a scale, but the radius here is 2 times r-opt. Right? So then my claim is the red disk that I've drawn completely contains the optimal disk. Let me just draw one more figure to illustrate this. We again draw some 5 points here. Again, this is the optimal disk. And this time, let me choose the red point very close to the center itself. And now again, let me draw a circle of radius 2 r-opt. Again, it's not to scale. So it's very easy to verify that if I pick up red point inside the optimal disk and draw a disk of radius 2 r-opt, then it will completely contain the optimal disk. Okay. And okay, and the key point here is because the red disk will of course contain at least k points, right? Because it contains the optimal disk. This red disk that we are showing here contains at least k points, and its radius is at most 2 times away from the optimal disk. So that's the key observation here. Let me write it down for you. So the observation is consider a point P inside the optimal disk. Then a disk of radius 2 times r-opt and center at P will contain the optimal disk and hence contain at least k points. That's it. So this was a key observation. I hope everyone's convinced about this. So now, based on this observation, there are actually two algorithms which can be presented. One is a deterministic algorithm, and one of them is a randomized algorithm. And I'll only present the deterministic algorithm here, and I'll leave the randomized algorithm as an exercise. Okay, so then Let's talk about the deterministic algorithm now. So this deterministic algorithm will try to mimic the observation that we made above. Okay, and how does it do it? Well, it will use a grid. We have spoken about grids before. So let's talk again about grids. Okay, so we look at our two-dimensional plane and again create grids here. I should draw them better. Okay, so what's the idea behind this grid? So you draw all the, first you draw these vertical lines such that the number of points which lie between any two vertical lines is k over 4, right? Between any two vertical slabs, k over 4, k over 4. Now, once you're done with this, now you draw, let me write it down, first vertical lines. Next, you draw these horizontal lines. Again, the same thing, k over 4 points will lie inside each. So let me shade it up. So there will be k over 4 points here. Similarly, here there will be k over 4 points. Right? So yeah, it's exactly the same way the way the vertical lines were drawn. Okay. So you can call this a combinatorial grid. We say this is a combinatorial grid because the spacing of the vertical lines and horizontal lines depends on the number of points, right? And not on the actual distance between the lines. So that's why we call it a combinatorial grid. So recollect that these points here were the grid points, the intersection of a horizontal and a vertical line. So how many grid points will there be? It's very easy to verify that it will be order of n over k whole square. Okay? Okay, good. So the next question that comes up is, how much time does it take to build this grid? So when we say how much time, we want to actually compute these horizontal and vertical lines. And for every point, we want to know which are the two vertical lines and which are the two horizontal lines which contain it. Okay. How much time does it take to build the grid? Means the horizontal and vertical lines. Horizontal and the so the claim is order of n log of n over k time to build the grid. Well, again, the proof, I'll leave it as an exercise. The hint I can give is recursion, right? I mean, okay, I don't want to reveal too many hints, but okay, let me not reveal too many hints. Let me just say recursion till you get all the vertical lines. Okay, so let me leave this as an exercise. It's a nice exercise to do. It involves solving a recursion tree or a recursion. Okay, so let's move ahead. Now, now just one final step is left and we are done with the algorithm. So let me have to draw the grid again. So let me do that quickly. Okay, and I'm not doing this well. Okay, so the next step is you look at every grid point treating each grid point as a center, compute the smallest disk containing k points. So this, for each grid point, this can be done in order of n time. Again, I'll leave this as an exercise. Right, so we're saying we'll take every grid point here, and then let's say k is again 5. Oops. So here points are dispersed like this. Oh, now you have to find the smallest, with this red point as a circle, find the smallest disk which contains 5 points, which I believe might be this. Anyways, you get the point, right? So you do this for every grid point. Every grid point here, do that. Everyone. And the claim is you can do this, find this smallest disk in order of n time for each grid point. Okay, and then final step, well, that's obvious now. Final step is report the smallest disk. Among all the disks that were computed here, and all of these disks contain exactly k points, you just report the one which is smallest. That's it. So how much time does this algorithm take? So computing the grid, as I said, takes n log of n over k time. And now the number of grid points I said was n over k whole square. And for each grid point, we computed the smallest disk with that grid point being the center. That takes order of n time, I said. Right, so the second term is the dominating term here. So this will be the running time. Okay, so what does this say? It says, okay, whenever k is large, the algorithm is faster. Larger the value of k, faster the algorithm. In fact, if k is close to theta of n, then order of n running time. Okay, good. So now let's do the analysis, right? I mean, okay, we did the running time analysis, we showed the algorithm, but why does this give a two-factor approximation, right? So we have to go back to the observation we made, which says that we actually picked a point inside the optimal disk, right? So proof of correctness, let's read that instead of analysis. Well, time to draw a grid again. So let me just focus on I'm not drawing the entire grid here. So let's just say that we're looking at the optimal disk, and let's say the optimal disk had its center here, right? And let's say, okay, let me just draw this first, or maybe let me write down something first. If the optimal disk intersects one of the grid points, then we get a two-factor approximation. Right? This is the optimal disk. And if this intersects one of the grid points, then based on the observation we made before, where was that? Yeah, the observation we made here. Okay, oops. The observation we made here, we get a two-factor approximation. Okay, so then that's the easy case. So let's assume that so now we are considering the other case, that the optimal disk does not intersect any of the grid points. Okay, so then how does it look like? All right, let's draw a picture now. Again, I'll not draw the entire grid, just the part that we really need. Right? Okay, again, this is where the center of the optimal disk lies, and the disk will look something like this because it doesn't intersect any of the grid points. This is the optimal disk, right? Okay, so then the question I want to ask is, how many points lie inside the optimal disk? Well, first, you can see this. The disk lies completely inside this vertical strip and inside this horizontal strip, right? And each one of them contains k over 4 points, right? So then, what's the answer for this? At most, k over 4 plus k over 4 is equal to k over 2. Well, but then that's a contradiction, right? Because this is the optimal disk which contains k points. But then if it does not intersect any of the grid points, we are saying it can contain at most k over 2 points. So clearly we have reached a contradiction, which means this case can never happen. The case that the optimal disk doesn't intersect any of the grid points can never happen, right? And because of that, the algorithm that we proposed of looking at all the grid points actually gives us a two-factor approximation. That's it, we're done. Let me just write that down. This is a contradiction since the optimal disk contains k points. And we are done. It's a very nice proof. Makes very nice use of the grid properties and very easy to follow as well. Actually gives us a good approximation as well, two-factor approximation. Okay, so that finishes the algorithm. So final thoughts. The running time actually is a bit high, right? The running time is n times this one, right? So for small values of k, this is pretty large. So this can actually be, so in the exercise, there's a randomized algorithm which will let you reduce this to this roughly. That's an improvement. And actually there's a more involved techniques of actually combining the grid ideas that we had from the closest pair problem, right? So if you can combine those ideas and there's some more heavy machinery, so what, which has to be used to actually come up with an order of n time algorithm. So it turns out an order of n time algorithm is possible, but it requires a lot more work. So yeah, so that's why I didn't go into that. And there's something called range searching, which if you're familiar with, even that can actually help you improve the running time significantly. So I'll post that also as an exercise. Okay, good. So that's all I had to say about this problem. Thank you.